Okay, welcome to my final project, which was to make a song within Python. And as you can see, there's hundreds of lines and very little of it is in Python. So I guess I'll start out by talking about sort of like how Python was used to import CTC sound, which is the main actual language necessary for creating music in Python. It was a little disappointing how little Python actually ended up in the project, but I mean, the majority of it's score lines, and there's still a lot going into sort of like how to get the library set up. Well, I don't know, you kind of just install C Sound and then figure out how to use an IDE that works with it, which VS does very well. But okay, so to get into it, we start out by importing the general system and then also importing CTC Sound, which is the necessary module for running any C Sound sort of musical operation. C Sound being the main language that people use to do code-based music. It seemed like the only feasible thing given Python doesn't have many sort of native oscillator creation options and stuff. So you start out by using this sort of massive string to define a CSD text file, and this is going to be the input that it will then run. So everything in here I'll get into in a second, but after we sort of define the CSD text, which includes the main components of the actual definitions of the project file right here, the definitions of each individual instrument, and what the score is doing to those, and then the actual score itself. So anytime you see definitions of like P4 or P5, those are positions within the 1, 2, 3, 4, 5 right here. I just specifies it's an instrument track. Regardless, I'm not getting into that now. So after we initialize that, we then have to actually kind of import the sound itself, or I guess create the instance of C Sound. And then after that, we sort of get our result for the CTC Sound project, which is the compiled CSD text function, is running that and taking this, which is this. After that, we have the sort of CS start function, which will actually start our performance, and then that takes us into a while loop where sort of while the performance has something to perform, then it will. So this is essentially saying that if there are actual events going on, then don't stop the performance. If there is nothing going on, then we can stop it. And if there's nothing sort of like queued up. And so then basically, yeah, right now, it's just going through the loop over and over and over again. After that, we have this cleanup function, which sort of deletes, closes out all of the audio and MIDI, stops any performance and things, and then we have to actually reset the C Sound performance with the next line. After that, we delete everything that was in there because I don't want it to just play on top of each other when we're running this multiple times. And then finally, this sort of little finish. And so if we actually go into the C Sound and how the code itself is made, that is going to be, so we start out with a sort of general, initializes the C Sound synthesizer, and then we have our options, so we're asking right here for a real-time output from it. Now we have to set the sample rate, which is essentially the amount of times per second that the computer is like making little points on each audio wave. This is how quality is ensured. It is a sort of like aliasing function for audio instead of visuals, as aliasing is usually done. Slightly complicated, but essentially this is the industry standard for audio today. After that, we have our maximum amplitude. We have, which will be used later when we're calling amplitude as a function for dynamics. Next, we have the number of channels, so we set 2 here for stereo. And after that, we have the samples in one control cycle, which gets into slightly more complicated audio stuff, but essentially think of it as related to sample rate. After that, we have our actual instrument definitions. And so I did a trio piece, which is for bass, alto, and soprano. The alto and soprano have some sort of interchangeability, but here's what's nice, where we can set, using different code, different kind of settings for the synthesizer. So first of all, we have to define what we're sort of controlling on things. We have a series of opcodes that start with I that are really helpful for this. So first things most important to note is the pitch and the amplitude. This is how we know how loud it is and what note is being loud. So we set those to the last 2 positions in the score line, which again is this. So this note, for example, will be playing a 73 hertz note at 0.1, one of the lower dynamics that we use. Actually, the lowest dynamic in the piece. Regardless, to keep going through, next we have our ADSR envelope settings, and ADSR is attack, decay, sustain, and release. It is the fundamental way that every sound is shaped with regards to the actual kind of way in which, I guess, a sound is heard. If you think about like a pluck tone that starts off with a pa, that would be a very sharp attack. Whereas if a tone went like then that would be a slow attack because it slowly starts at the beginning. The decay is then the amount of time it takes to get from the highest point in the attack to a lower amount, which is the sustain, so that a note kind of is sounded, if you think of a guitar string where it's a lot louder when you actually pluck it, and then it sustains for a bit. Decay is the time from that pluck loudness to the sustain loudness. Sorry if this is getting overly complicated. And then finally we have our release, which is after you let go of the note or the note stops playing, how long it still keeps kind of fading off for. Given every note sort of does that in real life, and if it was, because it's synthesized, if we just rapidly went to 0 right after, you'd get a bunch of really annoying clicks that sound gross. Next, we actually have to create an envelope out of these settings, so we use the MADSR opcode to do that. This is then going to be attached to the actual sound later, but first we have to define the cutoff frequency and resonance for the EQ. Resonance is essentially the degree at which a sound is cut. If you think of an EQ as a big spectrum of 0 to 20,000 hertz, then when you're cutting off a point, you don't want a flat wall, but you want a sort of curved line exponentially fading off. The resonance will adjust this, and it can even boost different frequencies as well. The cutoff frequency is where you're actually going to be cutting that, which is going to be far above any of our fundamentals and is nice for kind of mellowing out some of the synths. Bass has the furthest because I like its timbre when it's a bit more open. Next, we have the oscillator type, which I'm just doing a sawtooth oscillator. This is initializing the opcodes and sort of defining VCO as voltage-controlled oscillator. Next, we have to actually initialize our EQ by pulling it up within the Moog ladder function, and then doing this little, we take our VCO, we get the cutoff in the envelope, and then we have the resonance altogether, and then we are multiplying that to the output of each note, so that the note is shaped by the envelope. So every single instrument has some different settings. As you can see, the alto line has a bit of a slower attack than the soprano line and the bass line. Or sorry, the soprano line has the slowest attack. Then the alto has a bit slower of an attack. The bass is the sharpest, where I want it to be really plucky. They have slightly different sustains because I want the bass to sort of stay pumping through, whereas I want the alto to accentuate and the soprano to really stay as kind of a constant line. And then we have our different, I didn't go crazy on the different decay times, and then the releases are also pretty standard, except the bass is a really short release because bass tones flooding into each other, it sounds really, really awful. So now actually get to the score. So we have each instrument to find out with every single beat at which every single note plays at the exact frequency that I need it to play. You can see that the dynamics are sort of shifting around between sections, which I've broken it up into. Any dot indicates that it is the same value as came above it, so that's why I divided everything into individual instruments. I just have to define that once, and then we have dots coming down. So if we actually look, so here we have the instrument number, we have the beat on which it starts, the amount of beats with which it lasts, the velocity/volume of that note, and then the frequency. And I decided to round every frequency to the nearest whole number, because a lot of frequencies are decimals, to create a sort of odd tuning system that is only really achievable within this, because a lot of other tuning systems are based off of octave distributions, and with rounding, well, frequencies, how they work, they have an exponential sort of increase in the number that creates a pitch. If you like A5 is not just twice of A4, but several hundred more. It's interesting how that works, and so this one creates a lot more bass detuning, which then keeps the higher notes more in tune, which creates an interesting effect when you actually hear the performance. And yeah, every single instrument is their little sections that they play in, but I think it's about time, as we're getting to 9 minutes and 30 seconds, to play the actual performance for you. So, without further ado, here is my song that I created for this project, and then transcribed within this project. Some nice crunchy intervals. One thing that I forgot to explain really quick before I end this is that you have some different sort of shorthands that you can use within this other than just the dots, and that is there's one point where a note rises up to a high D and then has this really odd microtonal glissando downwards into an A, and that is occurring right here to the A, which is 440 hertz, using this operator, and that's how I got that weird non sort of regular microtonal glissando tone, which I think is another beautiful thing that comes out of the sort of affordances of working within this format. It's probably the least efficient way I've ever written music, but there are also, I think I approached it wrong. I think there's a lot of generative possibilities that require a lot more C-sound code that wouldn't really get into Python use as well, but is how I'm probably going to use it in the future with doing different, more interconnected sections rather than just laying everything out in all the beats it's going for. Yeah, there's a lot of interesting opportunities, particularly within the world of microtonal music, that I think will be fun to explore within it. And I really like how those intervals sounded. It might sound horrific and out of tune to you, but I hope you enjoyed. And that is my final composition. Thank you so much.